Thank you all for coming back. Let's start up again. Also, for those of you on Zoom, I'm now actually on that call as well, and so I will be able to see the questions coming in there. I'm sorry that I didn't track that in the first half. Thanks.
Okay. So before continuing as planned, I want to go back and correct two things from the previous section. So first, I claimed that the interventional distribution, the effect of intervening on X on the variable Y is identifiable in this graph. And my claim was correct. My derivation was not. So here is a correct derivation. It's messy, it's brief, but I believe it is correct. So I don't want to spend too much time on it, but quickly. So I'll start by writing the joint distribution over Y and Z given X as the following. So this is just using the decomposition that I get in the interventional graph, where I've eliminated this edge and marginalizing out U. And now I want to marginalize out Z as well, since I'm only interested in the effect on Y. So I just add the summation over Z. And now I'm going to introduce a summation over X prime, some other value of X, some over all assignments to X. So this is different than the fixed assignment to X that I'm trying to compute for the intervention. And I'm going to add in a term for the probability of X prime given U. And this summation I can do because summing over all X prime here, the sum's just 1. And then I'm going to add in to a numerator and denominator of what will become a fraction, a term corresponding to Z given X prime. Here's the probability of Z given X prime. So I'm just adding in the term that I need to be able to recover the joint distribution in the numerator here. After summing over X prime, after summing over U, I get that this is equal to the sum over Z of P of Z given X times a term that's the sum over X prime of the denominator. Sorry, yeah. Is that what I want? Okay. So as long as you're convinced that each of these steps is correct, then you should be convinced that this is a correct expression for the interventional distribution on Y given X, or sorry, the distribution or the effect of intervening on X on Y. Hopefully this example illustrates that this is in fact quite tricky to get right. And we want a theory that will allow us to do this in a systematic way. Sorry again about the incorrect derivation. The other thing I want to just mention again before diving in is this is the link for the handout. So this will contain pretty much everything I'm going to talk about and is a useful reference for definitions that you might not have caught or just want to remind yourself of at any point. Okay, yeah.
Feel free to decide to move on, but I'm still like confused about the question that was asked. I guess first about this, why that I can't have the identity map, like that yes. He can't speak. So,
sorry.
Do you mind saying that again, please?
Yes. So that was the other thing I wanted to address. So the question was, if this was the identity map, then doesn't this model just devolve or degenerate into the other model, which I said was unidentifiable? And the answer I said was no. And that's true. Well, sorry. Here, the issue is I need the distribution to be positive in order to be identifiable. That is, it needs to have full support. And so if this was the identity map, then it would not be positive, which in particular would mean I couldn't write this term depending on, or this term would be 0. And so I couldn't do this manipulation. And so it would not, in fact, be identifiable. So I actually need a positive distribution, which forces this to not be the identity map. So the result does not hold if this was the identity map, because it would, in fact, degenerate into the other model, which is not identifiable.
So as a follow-up question,
Mhm.
when we talk about like that some interventional distribution is identifiable, or whatever the word we use when we show that it can be decomposed into observable quantities, do we have a little asterisk that says like we assume that that these have a density that's not 0 anywhere? Like, are we making assumptions like that when we make claims like that?
I think we mostly are. I will try to be explicit about where we are, but if I don't say anything, assume yes. That's definitely safer. Okay. So that was all I wanted to say, correcting errors from last time. And now I will continue with the slideshow, with the presentation as planned. Okay, so last time we had introduced Bayesian networks and started to prove some basic results about distributions that are compatible with graphs. Now we're gonna do a more thoroughgoing characterization of the independencies that are induced by a Bayesian network. And we'll need a couple more definitions. So let's just motivate this with an example. So let's say we have this graph and a distribution compatible with this graph. What conditional independencies hold for any distribution compatible with this graph? So what about this? Are A and F conditionally independent given C and E in this graph?
Yes.
So yes. What about B and G given F? So yes.
Yeah.
What about B and F given E?
No.
So yeah, it turns out that this is not the case. And by the end of this hour, I'll have, I think, hopefully completed proving this to you. But it's a little bit subtle. That's the main point I want you to come away with, is that it's not, you shouldn't just think about it hard and try to determine it. You have to be systematic about it. And we're gonna talk about a systematic way of characterizing all conditional independencies that result in any distribution compatible with the graph. So we're gonna want another piece of notation. So we'll use this I sub prob for the collection of conditional independencies satisfied by a distribution P. And whenever I have a conditional independence statement here, it's assumed that all the sets of variables that are appearing are disjoint. And I make no claims about anything where they're not disjoint. Yes.
Well, one more question is we're now working with the Bayesian networks, and so there's no unobserved. Every variable is written down here.
Yes.
Okay, great, thanks.
So you can imagine you can imagine this Bayesian network comes from some causal model, and that this is unobserved, and we can still reason about conditional independencies, and that's in fact the power of this representation, is we can reason about conditional independencies without having access to all parts of the distribution, as long as we know where the edges are. Okay, so the first thing we're going to need is the notion of a blocked trail. So remember, a trail is a sequence of distinct vertices in a graph or in a DAG where each pair of adjacent vertices is connected by some edge, and the orientation doesn't matter. So a trail is said to be blocked by a set Z if it contains 3 consecutive vertices such that they constitute a chain that is, so I apologize, this A, B, and C does not refer to this graph, but if we have 3 vertices where A points to B points to C, or a fork, so that is a B that points to A and B that points to C in this trail, and B is in the set Z. So alternatively, a trail is blocked if it contains 3 vertices that form a collider, that is, A points to B, C points to B, and no descendant of B is in the set Z. So let's practice with a couple examples. So does the set B block this trail? Yes. So this is just the first clause. This is a fork. B is in the set Z. It even has the same name as in the clause. So yes. Okay, what about this? Does E block the BEF trail? Yes. So again, the first clause. Does the empty set block the BEC trail? Yes. No descendant of E is in the empty set. So yes. Okay, what about this? Does E block the B to E to C to F trail? No. Right. So, sorry, this edge is incorrectly, this edge should be swapped, but if you look at the trail in this graph, we start off with B to E to C, which is a collider. E is in Z, so this clause does not apply. And then the next 3 consecutive vertices are E to C to F. This is a fork, and C is not in Z, so it is not blocked. I apologize. This, well, that's just a wall. I shouldn't write on it. Anyway. Okay, does G block B to E to C? And here I've, of course, drawn the arrow in the correct direction. No, right? So here we again have a collider, and G is a descendant of E. So this condition is not met, so this trail is not blocked. So you might be concerned about the double negatives everywhere. We are going to have notation for a not blocked trail in a second. But the reason we care about blocked trails is because they're used to define dseparation, which will be extremely important, as follows. So let's say we have disjoint sets X, Y, and Z. We'll say that X is deseparated from Y by Z if every trail between any vertex in X and any vertex in Y is blocked. And in that case, we write X is deseparated from Y by Z in G. So this notation is remarkably similar to that for conditional independence, and that's not coincidental. And this is again why it's important to keep track of the subscript. So we use a subscript G for graph for the dseparation concept, and we use a subscript P for the probability concept. And if there is a trail from X to Y that is not blocked by Z, then we say that X and Y are deconnected given Z or deconnected by Z. And we'll call a trail that's not blocked an active trail. Okay, so with that said, let's take a look at this example again and try to figure out what deseparations hold in G. So are A and F d-separated by C and E in G?
Can you give us again the definition of the d-separation? My apologies.
Yeah. Well, I'll give you this will be a spoiler, but it turns out d-separation will correspond exactly to conditional independence in a sense that I'll make precise. So you can just think of it as conditional independence and you'll get most of these answers right if you're comfortable with conditional independence. But again, the definition of d-separation, well, I'll just return back to this slide. So a d-separation is any trail between any vertex in X and any vertex in Y is blocked. And blocked means any chain, or blocked means there's a chain with the middle vertex in Z, or a fork with the middle vertex in Z, or there's a collider and no descendant of the middle vertex is in Z. This is not an intuitive definition. We're going to spend a lot of time working with it, and hopefully it'll become easier over time. But yeah, let's look at this example and we'll see if we can get the hang of it a bit. So here, to check whether A and F are d-separated given C and E, we have to ask, is every path between A and F blocked by C and E? Sorry, every trail between A and F blocked by C and E. So let's first look at this trail, A, B, E, F. Is this blocked by C and E? Yes, because this BEF segment is a chain and E is in the conditioning set Z. Let's look at the other trail, A, B, E, C, F. Is this blocked? Yes. So this one is not blocked at this collider because E is in the conditioning set, but it is blocked at this fork because C is in the conditioning set. Okay. So is B and G, are B and G d-separated by F? So let's look at all trails between B and G. So there's a BEFG trail that's blocked by F. There's a BECFG trail, and that's blocked by F, again, because no matter whether we end the trail with EFG or CFG, we have a chain, and F is blocked in the chain, or sorry, F is in the conditioning set, so that chain is blocked. What about B and F given E? No. So this is the same example as before, I think, right? So the following trail is active, not blocked, between B and F, conditioned on E, the trail BECF, because the BEC collider is not blocked because we've conditioned on E, and the ECF chain is not blocked because we haven't conditioned on C. So this is a case where conditioning on E blocks one of the trails that connects B to F, but it doesn't block the other trail. And in fact, it activates the other trail, right? If we hadn't conditioned on E, and we were just looking at whether B and F were d-separated given the empty set, they would not be. They would be connected given the empty set because BEF would be available. But conditioning on E blocks this trail, but then activates this trail. So it's a subtle concept. We'll get a lot of practice reasoning about it, but are there any questions about the definition? Yes.
I don't want to take up too much time on it, but I have another question about the example that we started with on the left, which I may want to ask, and feel free to ignore it. We'll talk about it afterwards, but it's blocking me a little bit because I think that the way that I understood the causal diagrams was that there was the causal the tuple that we had was that Z is a function of X. And if it wasn't a function of X, it's a function of some other kind of U, I'd have a little dashed arrow to it. And if it's a function of X, I don't understand how we can possibly have, the probability of X, Y, Z is bigger than 0 for all possible X, Y, Z, because now I must be misunderstanding some.
Yes, so I think this is actually a point worth clarifying. So we're going to jump back to the beginning, but this is kind of important. So the question is, at the beginning of this segment, I mentioned that this can't be the identity map in order for this to be identifiable. But if Z is just a function of X, then how is it not, then where does, and these are both binary random variables, and well, how do I get a positive distribution here? And the answer is wherever you have, basically there are U's, background random variables, that only talk to one variable that are just not drawn. So you should imagine that X gets its own little private source of randomness, and Z gets its own little private source of randomness. Yes, sorry, private, UX, UY, and anywhere on the graph where you have an observable variable, there's an additional source of randomness that can be used to prevent each variable from being a deterministic function of, to prevent Z from being a deterministic function of X.
Okay, so okay, that makes total sense. I'm just writing down the ones that deal with 2 or more.
Yes.
I'm not writing down, but I guess I really can't deal with I really can't deal with Z is a function of X.
Things fall apart.
I really can't do that.
Yeah, so assume everything's positive for the time being and you'll be safe. Things fall apart if your distributions are degenerate in the way that you're concerned with. Okay, sorry. So let's jump back where we were. Dseparation. So we've done a couple examples. I would not be surprised if you're still not entirely comfortable with it, but we'll get more practice. Yeah, so I think I already went through this. So B and F are not deseparated by E because the BECF trail is active, even though the BEF trail is blocked. So to be deseparated, all trails between your start and end, or between your 2 quantities need to be blocked by the set Z. And we're going to use notation that is remarkably similar to that for probability for the set of all deseparations that hold in a given graph. And the reason we care about dseparation is that it gives us the answer we were looking for to what conditional independencies are implied by a graph. So here's a theorem. If X and Y are deseparated by Z in a graph G, then X and Y are conditionally independent given Z in all distributions P that are compatible with that graph. So dseparation tells you that the corresponding conditional independence exists for every distribution that's compatible with the graph. So here's a question: is the converse true? Where, well, I have to be clear about where I'm, well, here's what the other direction looks like. So if X and Y are not deseparated by Z, then there's some distribution P that's compatible with the graph in which X and Y are not conditionally independent. So of course, I could find a distribution P compatible with the graph in which X and Y are independent, because if I just have a distribution P that's created by just independently choosing every observable variable, then all conditional independencies hold, whether or not, and this distribution is compatible with every graph. So the best we can do is to say that whenever we don't have a d-separation, then we can find some distribution that witnesses conditional dependence between the variables that are not d-separated given the conditioning set. So is that statement clear? Okay, so we're not going to prove this right now, but I think we will by the end of this session. But we're going to start with a slightly easier question. And this is mostly a tactical decision to defer this because this is more involved than what we're going to look at right now. The question we're going to address right now is which graphs have the same d-separations? And then because of the theorem, which we'll prove later, this is the same thing as asking which graphs imply the same conditional independences. So here's the characterization, which we'll prove. And so we call two graphs, or we'll say that two graphs with the same d-separations are in the same Markov equivalence class. That's where the name of the slide and the name of this theorem comes from, but I won't use this terminology very much. But here's the characterization. So we'll say that G1 and G2 have the same or the theorem says G1 and G2 have the same d-separations if and only if they have the same skeleton and the same immoralities, to be defined in a second. But the first thing to make clear is I haven't written it out, but G1 and G2 need to be defined on the same vertex set. Right? They have to have some common vertex set, otherwise this won't even make sense. So what is the skeleton of a graph? It's just the undirected graph you get when you erase all the arrowheads from the edges. Right, so this is the graph G. The skeleton of the graph is just the undirected underlying graph. What are immoralities? An immorality is a collider. So again, a collider is a segment of three vertices where x of the form x, y, z, where x points to y and z points to y. Or in this case, BEC is a collider in which, so for a collider to be an immorality, it must be the case that the outer two vertices are not adjacent. So in this graph, BEC is a collider and B and C are not adjacent. So this is an immorality. And the claim or the theorem is that G1 and G2 have the same d-separations if and only if they have the same skeleton and the same immoralities.
So what's immoral about?
What's immoral about this? I don't know. Yes.
Parents not married. That's what's
Parents are not married. There you go. That's what's immoral. Is that the origin of the term? Okay. Is that a question or? Yeah.
Mathematical question. So adjacent means that B looks at C. We do not look about both directions.
So adjacent means there's either an edge between B or from B to C or from C to D. Adjacent is a. Sorry?
At least one. Is there any case that we could see both of them? No.
So we will not see. So we use shorthand of bidirected edges to represent unobserved confounders. But that is just shorthand and should not be taken to mean that there are edges in both directions, because again, we're only working with acyclic graphs, and if there were edges in both directions, we'd have a cycle. So for our purposes, the true edges in the underlying graph are always, we only either have an edge from B to C, C to B, or neither, but never both. Other questions? Oh, yes.
What's, just as an example, what's one arrow you could flip in this graph to and present the Markov equivalence?
That's a great question. That one, right there.
Okay.
Or that one. Or that one.
Okay.
So, let me go back. So sorry, for those listening in, the question was, what arrows can I flip in this graph and preserve the Markov equivalence, or preserve the d-separations, remain in the same Markov equivalence class? Those are two ways of saying the same thing. So I could flip this arrow, the A to B arrow, because I haven't introduced an immorality. And of course, if I'm flipping arrows, I'm preserving the same skeleton. There's still no collider here. There wasn't a collider there before, so I'm not introducing an immorality. Here, if I flip the B to D edge, I'm still not introducing a collider. If I flip the C to F edge, I'm also not introducing, or sorry, I am not introducing a collider.
You got rid of a collider.
Sorry.
Not an immorality, right?
Yes, so there was a collider here, but it's not an immorality because there's the C to E edge. And so I'm allowed to manipulate that collider. In particular, I can flip the C to F edge.
That's cyclic, isn't it?
Yeah.
Yes, sorry. I can flip the C to, thank you. So that would not be allowed because I've introduced a cycle. I could flip the C to E. I could not flip the C to E edge because I would then change the immoralities, right? Because B, C is an immorality. What could I do?
Flip the E to F edge? No, B and F. Oh, yeah,
Yeah.
okay.
Okay. Thank you for catching that. I will interpret that as evidence that you're paying attention. So, okay.
Just to be sure, can we inverse F to E, yes or no?
Yeah, so we cannot flip the F to E edge because even though it doesn't introduce a collider between E, F, and G, it would introduce a collider F to E to B, and that collider would be an immorality. So the resulting graph would have an immorality that's not present in the current graph. Okay, so we're going to prove this theorem. And in order to do this, we need a preliminary lemma, which is almost obvious, but not quite. So here's the statement. If two vertices are not adjacent in a graph, then they are conditionally independent, or sorry, they're d-separated in the graph given both of their parents. So when I am indexing variables by I or j, I'll just write parents of I or parents of j just to save symbols. So how can we prove this? How do we prove this? Well, we're going to do it as follows. Okay, so let's say we have xi and xj, and we're conditioning on their parents. So I'll just kind of draw that like this. We're conditioning on xi's parents, and we're conditioning on xj's parents. We need to argue that there are no active trails between the two of them. Or another way of saying that is that any trail between the two of them is blocked. So they're not adjacent. So there's no edge from xi to xj. So how could we build a trail between the two of them? Well, we can't have any trail that uses either of their parents because any such trail would be blocked by conditioning on their parents. So let's just assume for the sake of contradiction that we do have a trail connecting the two of them. So this edge cannot be oriented this way. V1 cannot be a parent of xi because then this segment right here would either be a chain or a fork with V1 in the conditioning set, so it would be blocked. By the same reasoning, this segment here can't be a chain or a fork, and so VK cannot have an edge into xj because then this triple here would be blocked. So we know that if there is indeed an active trail, as we assumed for the sake of contradiction, then the edges from xj, then there must be an edge from xj to the vertex immediately preceding it, and there must be an edge from xi to the vertex v1. Okay, and now, if that's the case, there must be a collider somewhere in the trail. Right, we have one edge pointing this way, another edge pointing this way. At some point in the trail, we must switch from pointing this way to that way. So there has to be a collider. Okay, so let W be the first collider that we run into as we're walking from xi this way. So another way of writing this is using my squiggle notation, which looks great in LaTeX, but I can't draw it at all. Right, so there's a directed path from X to W, the first collider that we encounter. And let Y be the first collider that we encounter going in the other direction. Yeah, sorry. I wrote X here, what I mean is XI, here I mean XJ, and here's Y. So if there's only a single collider on the trail, then W equals Y. And now for the trail to be active, this collider has to have some descendant in the conditioning set. But the conditioning set is just the parents of I and the parents of J. And so any descendant of, let's say W, in the case where W equals Y, has to be either a parent of I or a parent of J. And in either case, let's say we have a descendant here that is a parent of I, well, then we have a contradiction, right? A parent of I can't appear as a descendant of I. That would be a cycle. And neither can we have W having a descendant that's a parent of J, because then if W equals Y, right, then we have a path here from XJ to a parent of J, which is also a contradiction. So that can't happen. So the only case left is where W does not equal Y. And here it's allowed for Xi to have a descendant, which is a parent of J. That's fine. So maybe this collider is activated by a parent of J. This collider is activated by a parent of I. Right, that's okay. But in that case, we have that Xj comes before I in the topological order, or in any topological order. Namely, Xj has I as a descendant, and Xi has Xj as a descendant. That's a contradiction. We have a cycle. So this can happen, and we conclude that Xi and Xj have to be deseparated given our condition on both of their parents. So this may seem like a lot of trouble to go to for a little lemma, but it's going to be worth it because it will allow us to immediately prove the following direction of this Markov equivalence characterization, which is that if G1 and G2 have the same d-separations, then they have to have the same skeleton and immoralities. So why is that? Let's look at the following case. So first, what if they don't have the same skeleton? what if G1 has some edge that's not present in G2? And in particular, let's just say there's some X to Y edge present in G1, but not in G2. I claim that then X and Y are deconnected in G1, conditioned on their parents, and they're deseparated in G2, conditioned on their parents. And the reason for this is just by the previous lemma, X and Y are definitely deseparated in G2, conditioned on their parents. And then we have a direct a trail in X to Y, a single edge that is active, conditioned on both their parents in G1. So this contradicts our assumption that they have the same deseparations. So it can't be the case that they have the same deseparations, but have different skeletons. So we've ruled that out. What about immoralities? So let's consider the case where G1 and G2 have the same skeletons, but different immoralities. And they somehow have the same deseparations. Can this happen? So without loss of generality, let's say that G2 has this immorality and that it's somehow not an immorality in G1. But because their skeletons are the same, the edges must be present. They just must be reoriented or oriented differently. And now for this to be an immorality, in G2, it must be the case there's no edge from X to Y or Y to X. Right? That's what it means to be an immorality. It's a collider with where X and Y are not adjacent. So apply the same lemma again, condition on both of their parents. These are deseparated. But clearly, conditioning on the same set of vertices, which do not contain all the parents in of Y, for example, in this picture, we get that X and Y are deconnected on the left, right? So if so this immorality and this so in G2 they're deseparated, conditioned on the parents of X and the parents of Y. In G1, no matter how we change the edges here to ensure that this is not an immorality, these are going to be deconnected, because as long as it's not, the only way for this to not be an immorality when this edge is missing is for it to either be a chain or a fork. And in either, to either be a chain or a fork, and in either case, this path is going to be active, conditioned on these parents. Any questions about that? So the conclusion is, if G1 and G2 have the same deseparations, then they have the same skeleton immoralities. Yeah, so here you can see, no matter how we get a graph without that immorality on the left, we're still going to have X and Y deconnected, conditioned on the same set. Okay. So to prove the converse is going to be a little bit more difficult. So this is that if they have the same skeleton and immoralities, then they are deconnected. If they have the same skeleton and immoralities, then they have the same deseparations. So we need the notion of a tight active trail. And I'm going to put this on the board. So what is a tight active trail? So a tight active trail it's going to be an active trail that's minimal in the following sense. So it's a trail B1, BK, such that no subsequence vertices in the trail is active between the same start and end. right? So I can't just do a shortcut where I skip V2, for example, and go V1, V3, all the way up through VK and get an active trail. And there should be no way to move things down in the following sense. No active trail. W1 or WK such that WI is in the descendants of VI. So I can't take this active trail and replace everything with descendants and some WI does not equal VI. So is this definition clear? So a tight active trail, it's an active trail where you can't just find a shortcut and skip some vertices, and you can't replace vertices with descendants and also get an active trail. So first,
Can you remind us what
an active trail.
means? Yeah.
So an active trail is a trail that is not blocked.
Okay, great.
So an active trail is proof of deconnection, and no active trail is proof of deseparation.
You will eliminate the second condition.
Not with the proof that I'm going to present.
Illuminate.
Oh, illuminate. Sorry, I thought you asked if I could eliminate it. I wish I could eliminate it. Illuminate it. Not particularly. I don't have a great. So this definition is constructed so that I can prove this claim. It's not. It won't really be useful in any other context. Yeah.
So is the idea of a tight active trail just that whenever X and Y are deconnected,
There is not actually necessarily a unique tight active trail, but it's just going to be a kind of canonical example of a trail, or well, it's going to be a kind of trail where I can easily reason about what its structure is. And so here's the first observation. If they're deconnected, there is a tight active trail between them. So if X and Y are deconnected by Z, there is a tight active trail witnessing that connection. So here's the proof. Start with any active trail and repeatedly check, can I find a subsequence of vertices in this trail that preserves it being active? If so, replace it with that. Then check, is there any way to replace any vertex with a descendant of it that preserves it being active? If so, replace it with that. There are only a finite number of trails in a finite graph. So eventually I'll run into some trail that I can't improve in any way, and that will be a tight active trail.
You're going to get an example.
Sure. Let's see. So I'll give you examples of things that are not tight active trails, and hopefully that'll be helpful. So here's X and Y. If my graph looks like this, X to W to Y is not a tight active trail if my conditioning set is empty, because I could just drop the W vertex and go directly from X to Y. If my trail looks like this, and W2 is my conditioning set, the trail X to W to Y is active because I've conditioned on W2, so that activates this collider. But this is not a tight active trail because I could replace W with W2 and replace the trail with X to W2 to Y, and that's also active. So this violates the first condition. This violates the second condition. So the x to y is tight in the first, x to w2 to y is tight in the second. So why bother with this definition? Because we get the following lemma. So the lemma is the following. So if I have a tight active trail relative to some conditioning set Z, then whenever I have a shortcut, that is, I have xi minus 1 has an edge to xi plus 1. Then it must be the case that I have a fork and either xi minus 1 or xi plus 1 is a collider. So I'm looking at the time and realizing I'm going slower than I had expected. So let's see. I'm going to skip the proof of this lemma, even though it is the whole reason for having this definition. And I'm going to skip directly to the application of this lemma. And I should mention quickly, if xi is a collider in T, in this tight active trail, then it must be an immorality. That's a corollary of this. By the contrapositive, I think. So how are we going to use this? So the proof, by the way, is in the handout, so please do refer to that as needed. Okay, so let's prove this direction of the claim using this lemma, which I will remind you of its statement when I use it. So let's fix G1 and G2 with the same skeleton and immoralities, and let T let T1 be a tight active trail between the tight active trail between X and Y conditioned on Z. And let T2 be the same trail in G2. So we're going to show that this trail is also active, and that will imply the conclusion. So let's just pick 3 vertices along the trail and show that that 3 vertex segment is also active in G2. If we can do this for any segment of vertices along the trail, then we're done. Okay, so here's our segment. First observation. Let's consider the case where this is not a collider in T1. Sorry, in G1. It's not a collider. So then it also must not be the case that it must also be the case that this is not a collider in G2, because sorry, if this edge is present, then my claim is not being a collider here in G1 implies also not being a collider in G2, because otherwise, no matter sorry. What am I? Sorry, if it's not adjacent, excuse me. If this edge isn't present, then I can't have a collider in one and not a collider in the other, because that would be an immorality in one that's not present in the other. That's all I wanted to say. So, but what if they are adjacent? What if xi minus 1 is adjacent to xi plus 1? Then we know by this lemma that Flash didn't prove that this must be a fork. So I have to take my word for it. And then that forces one of one of xi minus 1 or xi plus 1 to be a collider by the second part of this lemma. And then it must be an immorality in G2. So the reasoning is again as follows. If this edge is present in both graphs, but we have a and so we have a fork here by the lemma, then we have a collider either here or here by this lemma, and then that must be an immorality again by the lemma. And then that allows us to conclude that xi is not a collider. I apologize, this reasoning is a lot less clear if you haven't absorbed the statement of the lemma. Let's move on to the next, to the more interesting case. So let's consider the case where this is a collider in G1. Okay, so now by this lemma and its corollary, because this is a tight active trail, this is an immorality. So that's kind of the power of the definition of a tight active trail. Is any collider is an immorality. And okay, and because it's an immorality, it's also present in G2. And now, so let's consider some cases. So what if xi is in the conditioning set? Then the trail segment is also active in G2. Right? If I have the same conditioning set and I have an immorality and I condition on the collider, then it's active in both graphs because the immorality is preserved. So the only way this could go wrong is if in G1 I have some descendant of xi that's in the conditioning set, but in G2, because I've flipped some edges around, I've lost the path to a descendant that makes this active, right? So so let's say I have some descendant here, W, that is in the conditioning set, but somehow it's not in a descendant of xi in this other graph G2. Well, my claim is going to be that this path here doesn't contain any colliders in G2. So let's call this S. And suppose that in G2, somehow we ended up getting a collider here, that we flipped some edges around. And in particular, let's say, we flipped something that looked like this to this into something that looked like this, and we generated a collider. Then we must have that A, and so let's call this A, B, C. So this is a zoomed in segment of this path and I'm looking at it in G2. Well, because this was a tight active trail, and because G1 and G2 have the same immoralities, we know that A and C must have been adjacent in G1, right? Because otherwise I'd have introduced an immorality in G2 that wasn't present in G1. And then because of the direction of the edges, right? In G1, we had A to B to C. We must have that the missing edge goes from A to C. Otherwise, we'd have a cycle in G1, sorry, in G2. Okay. And now my claim is that if I am considering the shortest directed path here, sorry, back here, my claim, or I didn't spell this out as much as I should have, but I wanted W to be the vertex in Z that was reachable by a shortest directed path. And if I chose it that way, then I can't have this shortcut present, right? So this situation can't happen because then I could find a shorter path where I skipped from A directly to C. Okay, so the remaining case, so I can rule out the presence of a collider in G2 along this path, because if that happened, I could find a shortcut in G1, contradicting my choice of the path. So the remaining case, the only way that this could go wrong and deactivate the path in G2 is if the very first edge right out of Xi was flipped between G1 and G2. So let's draw the resulting picture. So in G2, we'd have this. And let's call this vertex W prime. And sorry. Where is the correct read? Okay. Yeah, okay. So we have this picture. And then since the colliders xi minus 1 xi w prime and w prime xi plus 1 are not present in G1 by assumption, it must be the case that these are not immoralities, because if they were, again, then they'd have different immoralities. So we must have that this edge and this edge are present in both of the graphs. And by acyclicity, right, they can't be, they have to have this orientation, because in G1, the path goes this way and then down. And so we end up with the following picture. And this exactly contradicts the claim that our original thing was a tight active trail, because in G1, we could have replaced xi with w prime. So the conclusion is that there are no colliders on the trail from xi to a descendant in Z in either graph, G1 or G2. And so in G2, we have the same picture, and this segment remains active. And we've taken an active path in G1, an active trail in G1, and found that it's also active in G2. So these tight active trails, they are a subset of trails that are preserved under these Markov equivalence classes. So that's one way of thinking of them. Anyway, since this was arbitrary, we conclude that that the whole trail is active, and then, right, so we've taken any active trail and any tight active trail in T1 and proven that there's that the exact same trail is active in G2 if G2 has the same skeleton and immoralities, which proves the conclusion. Okay, so modulo the lemma, which I didn't prove, I have now established that two graphs with the same vertex sets and the same skeleton and immoralities have exactly the same d-separations. I think that's time, or a little bit over time. And so after lunch, I'll come back and show that dseparation actually corresponds to conditional independence, and then we'll move on to the specifically causal stuff and the do calculus and the ID algorithm. Okay, thanks.
You're on your own for lunch now, and we reconvene at 2.